We spent a lot of time recently talking about graphs of straight lines, graphs of linear functions, which if you think about it, a linear function is really just a polynomial of degree 1. So what we're going to do today is move on to section 2.3, quadratic functions, and I guess we're taking the next natural step here. Instead of looking at polynomials of degree 1, we're going to move on. A quadratic function is a polynomial of degree 2. So we're going to look at functions of this type. And just to be very precise, that is, a quadratic function is a function that can be written in this form. So f of x is ax squared plus bx plus c, right? It's a polynomial of degree 2, where once again, if you want to be degree 2, you have to specify that a in particular is not 0. Otherwise, this term would go away and you'd be looking at degree 1. And of course, a, b, and c are just constants. They're real numbers. So a is, in fact, this number here, a, is really important in determining the shape of the graph. And it turns out all quadratic functions basically have the same shape. They're all parabolas. So the graph of a quadratic function is a parabola. And in particular, that parabola opens upwards if a is positive and downwards if a is negative. Is a parabola that opens upwards if a is bigger than 0 and downwards if a is less than 0. So in general, here's the two shapes you're looking at. Here's my parabola. Right, this is the general shape of a parabola. And this is the upward opening case, so here's the a bigger than 0 case. Or I have a parabola that opens downwards. Something like this. Here's the a less than 0 case. Alright, so the graph of a quadratic function always takes on the same shape. It's always this parabolic shape. And a, all we have to do is look at this number a, this coefficient in front of x squared, ask yourself, is it positive or negative, to know whether your parabola opens upwards or downwards. Of course, I can shift this all around the plane, I can stretch this out, shrink it a bit, but it's still always the same general parabolic shape. Now in every parabola there's one very, very interesting point. It's in the a bigger than 0 case, the upward opening parabola case, it's this point right here. It's sort of the bottom of this valley, the bottom of the parabola. It's the minimum value the function ever attains. So let me just give this some coordinates. How do we call this? H and k. So that has coordinates hk. And we'll do the same thing over here. For the downward opening parabolas, we've got the peak of this mountain, the top of the parabola, the maximum value the function ever attains. We'll give it the same coordinates, we'll call it h and k. And in both cases, it's called the vertex of the parabola. So the vertex with coordinates h and k of the parabola is the point where the maximum, so maximum happens in a less than 0 case, where the maximum or minimum, in this case the a bigger than 0, where the maximum or minimum value occurs. And what is that maximum or minimum value? Well, it's the y value, right? The y values are the outputs of the function. You plug in x, you get out y. So in both cases, the maximum, in this case, the maximum value is k, or in this case, the minimum value is k. So either way, when I talk about the value, I'm talking about equals k. But there's a problem. The problem is the standard form I've given you, ax squared plus bx plus c. Yes, it's sort of the standard form for a quadratic, But the only real interesting information you can read off of that is A. You can read off, does my parabola open upwards or downwards? It makes it really difficult to read off, where's my vertex occurring, right? Where is this very interesting point that all parabolas have? Where is the vertex? And in order to answer that question, we're actually going to change the form. We're going to write our quadratic functions in a different way. So if you're given a quadratic function in standard form, f equals ax squared plus bx plus c, we can always do this trick called completing the square. I'll talk about it in just a second if you've forgotten how completing the square works. But we can always complete the square on this to turn it into an alternate form. This is to turn it into a form that looks like this. F of x equals a times x minus h squared plus k. And this is sometimes called the vertex form. And this form is really useful because these two numbers that you get out here, h and k, those are the coordinates of the vertex. So you can literally just look at the form and read off, where's my vertex? The vertex is at the coordinates hk. And we still have the same a as before. This a that I have listed here, it's the same a as we started with, so it's the same a, meaning this a that you look at still tells you, does my vertex or does my parabola open upwards or downwards? Alright, so it's the same a, so a positive means upwards, upward opening, and a negative means downward opening. So this new form allows us to read off, just looking at the form of it, we can just immediately read off lots of interesting geometric information about the parabola, or the graph of this function. Where is the vertex and does it open upwards and downwards? So let's do an example. Let's complete the square on something. Okay, so here's our first question. We're given a quadratic function in a standard form. Minus, in this case, a is minus 2, b is 16, c is minus 24. And the question is, convert this to vertex form. So we always go through the same three steps. Here's the steps. First one is factor out an a. So look at our a term and factor it out. Except I'm not going to factor it out from all three. I'm just going to factor it out from the terms that have an x in it. So we'll factor out the minus 2, and we're looking at x squared. Pulling a minus 2 out of 16 leaves us with minus 8. Minus 8x minus 24. Okay, so this was the first step. Just factor out an a. Factor out a, so the coefficient of x squared. Factor out a from the first two terms, or the terms with x. The terms. Let's call them the non-constant terms. How about that? So everything except the constant term at the end. From the non-constant terms. Alright, so there's the first step that you always do. Second step, now I want to complete the square. So here's what completing the square entails. The question is this: what number do I need to add right here to turn this into a perfect square? Something so that when I factor this, this will be x plus something squared, right? And the answer is, it's sort of the same formula every time. The number I need to add here is going to be, we look at this coefficient, so minus 8, and I take half of it, so half of minus 8 is minus 4, and then I square that. So take half of minus 8 minus 4, then I square minus 4 to get 16. Turns out that's what I need right there, 16. 1/2 of this coefficient squared. So complete, next step, we'll stick to the red. Complete the square. So this is half of x coefficient, squared. Alright, so we took 1/2 of minus 8 to get minus 4, squared it to get 16. Now here's the other problem. I need to balance this out. I can't just go adding numbers to my function and not expect to change the value, right? If I add this, I need to subtract it off as well. So what am I really doing here? If I add 16 on the inside, I didn't have this before, I've thrown the 16 on the inside, well that 16 is multiplied by minus 2. Alright, so I've added negative 16 to this entire function. Or sorry, not negative 16. 16 times minus 2, negative 32. So I'm subtracting off 32 from this entire function. To balance that out, I need to add 32 to the entire function. Do you see how that works? So if I throw the 16 in here, I'm really subtracting 32 from this entire thing. To balance that out, to keep it sort of equal to what I started with, I need to add 32 as well. So I'm minusing 32 and then adding 32. So this is my just balancing term. And that's important. And step 3 is now this is in vertex form. Once I write this as a perfect square. So as long as we add the right term here, the right constant, this will always be a perfect square. In this case, this factor is exactly as x. Multiplies together to give 16, adds together to give minus 4, or minus 8 is x minus 4 squared. Minus 24 plus 32 plus 8. And you'll notice this is now in vertex form. This is of the form a times x minus h plus k. So if I wanted to read off some interesting information, vertex is at minus h, so 4 plus k, 4 and 8. Vertex is at 4 and 8. And it opens, because a is negative, a is equal to minus 2. This implies it opens downwards. And if I wanted to do a very quick, very rough sketch of this, so a very quick, very rough sketch, maybe I'll call this 4, let's go up to a point that maybe I'm calling 8. There's my vertex, and it opens downwards. So very roughly, that's what the graph looks like. If I want to be extremely precise, there's a few more things I need to calculate, which we'll do in a future example. But I need to figure out where these x-intercepts are and where these y-intercepts are. And then I'll have a really, really accurate sketch. In fact, we'll do that in this next example. Alright, so here's a quadratic function. X squared plus 2x minus 5. And I want to do a really full analysis on this. So I'm not going to write down all the different parts of the questions, but we're going to answer a lot about this as we go. So let's sort of fully geometrically analyze this. So first thing I need to know is, of course, a is positive, so I know it opens upwards. But if I want to find the vertex, I need to put this in vertex form. So let's complete the square on this. First step is factor out a, the coefficient of x squared. Well, we have a 1 here, so there's really nothing to factor out. So this is just going to be x squared plus 2x plus or minus something minus 5. What does this something need to be? Well, remember what we do. We go into the coefficient of x, so 2. We take half of that. Half of 2 is 1, and then we square that. 1 squared is 1. That's what I need to add right here, plus 1. Well, if I'm adding plus 1 to the equation, I need to subtract off 1 to balance it, so minus 1 on the end. And this is indeed a perfect square now. This is now x plus 1 squared minus 6. So where's my vertex? Vertex is at, here you need to be careful. It's not at 1 and 6. Remember the vertex form is x minus h. So you can think of this as plus 1 is minus 1. Alright, so my h is in fact minus 1 here. So the vertex is at -1. And do I have -6? I do have -6. So -1 and -6. All right, remember it's x minus h plus k, so this is, again, if I'm going to be very formal here, plus -6. So there's my vertex. Again, I know A is 1, it's positive, so it opens upwards. Opens upward. And let's be very precise with our sketch here. So I indicated last time that we need to figure out where the x-intercepts and where the y-intercepts are. All right, so I have something like this. I have so far that my vertex is at -1 and -6, so there's -1, and we'll say this is -6 down here. So there's my vertex. I know this parabola opens upwards because A is 1, so it opens upwards, something like this. And more or less that's what the graph is going to look like. But let's indicate what some of these points are. I'm looking at the graph and I know I should have 2 x-intercepts and I should have a y-intercept. So let's try and find them. Y-intercepts. How do we find the y-intercept? Well, the y-intercept happens when x is 0, right? It's just the output of the function. We plug in x equals 0 and we output this y value of the y-intercept. So we're just plugging in x equals 0 to get this. You can go to either one of these functions, either one of these forms. How about we go to the vertex form? It's in fact easier to use the first one, but we'll plug this in. F of 0 is 0 plus 1 squared minus 6. Well, that's 1 minus 6. That's minus 5. So our y-intercept right here is happening at -5. I also expect, based on the graph, you don't always have x-intercepts, but based on this graph that I've sketched, I know that I should have two x-intercepts, so let's try and find those. Life is a little bit easier if we start with the original form here. So I'm actually going to erase the vertex form. We'll start with the standard form. I believe we have x squared plus 2x. Okay, so here we're looking for the x-intercepts, which are sometimes called the zeros of the function. Why are they called the zeros? Well, because they're the x values that you plug in to get an output of 0. It's when y equals 0, right? So the x-intercepts or zeros is when y is 0. So we're trying to solve, what does 0 equal x squared plus 2x minus 5? Well, we've done this already. This is solving a quadratic equation. We can either try to factor it or go to the quadratic formula. It looks like it factors though. It looks like this factors as multiplies together to give minus 5, adds together to give 2, I take that back. Yeah, this doesn't look like this factors, right? Two numbers that multiply to give minus 5, it's either 5 and 1, and those aren't going to add together to give 2, so we're not going to use factoring here. We're going to go to the quadratic formula, which says x is going to be minus b, so minus 2, plus or minus the square root of b squared, so 4 minus 4ac. 4 times 1 times a minus 5. All over 2a. 2 times 1. And this is minus 2 plus or minus the square root of 4 minus minus, so plus 20, square root of 24, all over 2. You'll notice I can clean this up. I can make this look quite a bit better. This is minus 2 plus or minus. 24 is root, 24 is 4 times 6. So root 4 is 2 times root 6, all over 2. And then since both terms up top are multiplied by 2, and I've got a 2 down below, I can cancel these to get 1 plus or minus root 6. So those are my two x-intercepts. Obviously the one on the right here is 1 plus root 6, and then the one on the left is 1 minus root 6. What else might you want to do with this? Someone might ask you, what's the, so we've already answered this question, where's the vertex? The vertex is at minus 1 and minus 6. We've answered the question, does it open up or down? We've found the x-intercepts, the y-intercepts. Someone might ask you, what's the domain and what's the range? Well, the domain is all the x values you're allowed to plug in. And remember, as long as I'm not dividing by 0, as long as I'm not taking square roots of negative numbers, I'm allowed to plug in every number. So quadratic functions, the domain, what x values am I allowed to plug in? Well, all the x values along the x-axis. So the domain of quadratic functions is always all real numbers, minus infinity to infinity. What about the range? Remember, the range are the y values you output. It's the possible outputs of the function. So if I look at this function, what y values do I hit? What y values do I sort of attain? What do I output from this function? Well, I output every single y value that lives above the vertex, because the vertex is at the bottom of the parabola. So I'd output every single y value from minus 6 off to infinity. It's everything above the vertex. So the range is minus 6, including minus 6 with a square bracket, because we actually do output minus 6 right there when you plug in negative 1. Minus 6 off to infinity. And there's one more thing people might ask you. What's the minimum value of this function? What's the minimum value? Well, it's the y value of the vertex, because we're opening upwards. Our vertex corresponds to a minimum, so our minimum value is minus 6. Meanwhile, our maximum, if we had a downward opening parabola, we would have a maximum value, but upward opening parabolas don't ever have a maximum. Right? There is no largest output. It just goes up to infinity, because our range goes off to infinity, so there really is none. And of course, this is just one example, but this is sort of a full analysis of how these work. Just about everything you could be asked about these questions. If you want to answer questions about the graphs or geometric information, about where's the vertex, what's the minimum value of a quadratic function, this is what you should do. Put it in vertex form, and then you can read off everything that you need to know. So here I want to go backwards. Instead of giving you the equation and asking you to find geometric information about the graph of the function, we're going backwards. I'm giving you geometric information. I'm telling you we've got a quadratic function that has vertex of 2 and minus 1, and it has y-intercept of negative 3. The question is, find the quadratic equation that realizes this function, or this graph. Well, what do we know? We know all quadratic functions have a vertex form, so it must look like this. It must look like a times x minus h squared plus k. So it has to take on this general form. This is just the vertex form of a quadratic function. And I know that for this particular function, I want it to have vertex 2 and minus 1. So I know that h is 2 and k is negative 1. So we'll plug that in. So now it looks like x minus h, x minus 2 squared plus -1, so -1. So we plugged in for the vertex. The only thing left is, what's A? Well, there's also only one little bit of information that we haven't used. It's that the y-intercept is -3. So what's the y-intercept? Well, the y-intercept, this tells me that when I plug in x equals 0, my y value should be -3. So let's plug this in. This means when I plug in x equals 0, my y value should be -3. So I'm claiming that this is a solution to this equation. Right? The points on the graph are solutions to this equation if you think of it like that. So let's plug them in. If y is -3 whenever x is 0. So this means, I think we can solve for a now. I think we have enough information here. We've got -3 is equal to -2 squared 4a minus 1. And we should just have to isolate a now. So let's see, let's add 1 to both sides. 4a is equal to -2. I'm just changing the order here. If I add 1 to both sides, I would have -2 is equal to 4a. Well, that's the same as saying 4a is equal to -2. And this, of course, means dividing both sides by 4 is a is -2 over 4, or -1/2. So that's it. We started off with these three unknowns. We started off with not knowing what a should be, what h should be, and what k should be. But because we were told the vertex, we know h and k. And by going through this trick, by knowing what the y-intercept was, we were able to figure out what a should be as well. And therefore, our final answer is y is equal to -1/2 times x minus 2 squared minus 1. So this is an example of sort of going backwards, being given geometric information and finding the function. And you should be able to go both ways. So if someone gives you a function, you should be able to identify what the graph looks like, all of the geometric information. But you should be able to handle both directions. Let's do something else with this. Let's solve an inequality. So here's an inequality. It's solve this following inequality. Solve x squared plus 7x plus 12 is bigger than or equal to 0. We've solved inequalities already, but they were linear inequalities, and because they're linear, they're much easier to solve than quadratic inequalities, or even higher degree polynomials, or inequalities involving higher degree polynomials. In general, are quite difficult, but with quadratics, there's a trick. And the trick is to realize that because the shape of this function is a parabola, this isn't that bad. So let's just look at this. This is a quadratic. I'll show you what I have in mind here. This is a quadratic. And because a is positive, a is 1 in this case, it opens upwards. So in general, it's going to look either something like this, in which case, when is it bigger than 0? Well, the output's always bigger than 0, right? This is think of this as the y values, it's the outputs of the function. If it looks like this, then the answer is it's bigger than 0 for all real numbers, from -infinity to infinity. But the only other possibility is it cuts through the x-axis. In which case, when is it bigger than 0? Well, it's bigger than 0 to the left of this x-intercept, and it's bigger than 0 to the right of this x-intercept. So what I really need to know is, what are the x-intercepts of this function? What are the zeros? That's the most important thing here. This is all I have to identify. So what are the zeros? Well, we'll solve this. When is x squared plus 7x plus 12, when does it equal 0? Unlike the last problem, this looks like one we can't actually factor. This factors as two numbers that multiply together give 12, add together give 7, x plus 3, x plus 4 equals 0. So the only way two numbers can multiply to give 0 is if one of them or both are 0. So either x plus 3 is 0, which means x is minus 3, or x plus 4 is 0, so x is negative 4. So this particular parabola does indeed have two zeros. It has a 0 at, my picture doesn't look quite like this, let me redraw it. Looks a bit more like this. It has a 0 at minus 3. Obviously this is not to scale or anything. And a 0 at minus 4. So when is the function less than 0? Well, it's less than 0 along here. So from minus 4 to minus 3. When is it bigger than 0? It's bigger than 0 everywhere else. So our solution set looks like, on the real number line, it's everything along here up to 4, minus 4. So minus infinity, oops, sideways 8, minus infinity to minus 4. And because we're allowed to include 0, this isn't strictly bigger than 0, this is bigger than or equal to 0. It's equal to 0 at minus 4, so we're going to throw it into the solution set. We'll do a square bracket. And it's bigger than 0 from minus 3, including minus 3, off to infinity. So also from minus 3 to infinity. And the solution set is both of those intervals together. So the mathematical notation here is the set union. So there's the union of those two intervals. But the way you should read this is this interval and this interval is when it's bigger than or equal to 0. Again, in general, solving inequalities can be difficult. In the linear sense, it's quite a bit like just solving a regular equality. But once you start getting to more difficult inequalities, in this case parabolas, or not parabolas, quadratic functions, life can become a bit more tricky. But the idea here is to realize that, oh, well, since my graph always takes on this parabolic shape, there's really only two things that can happen, is it cuts through the x-axis or it doesn't. And as long as I can figure out these 2 points where it cuts through the x-axis, then we've solved the inequality. We'll do one more example. So here we have two different functions. Notice the first one is indeed quadratic if I just expand it out, and the second one is this linear function. And I'm telling you the domain here, we're going to restrict the domain. Instead of thinking about all real numbers, we're just going to allow x to range between 0 and 10. So we've got these two functions. The question is, A, let's I'm gonna set this up a little bit out of order from the way you'll see it in the homework, but here's what I want to do. I want to solve f of x equals g of x. Ask when these two functions equal to each other, and we'll do this to 2 decimal places. Because I want to plot the graphs of both of these things on the same coordinate axis. And the way I'm going to do that is by solving this equality. I need to know this first. So we'll pose this as two questions together. And graph f and g in the same coordinate system. Okay, so I want to know when these two functions are equal to each other. How do I do that? Well, I set them equal to each other and I solve the corresponding equation. So here we go. When is minus 0.4x times x minus 10, when do you equal 0.3x plus 5? I have an equation, I need to solve for it. So let's see, we want to solve for x. So we'll probably want to expand this side out first. 0.4x squared minus 0.4x times minus 10 is going to be plus, this one's easy, plus 4x multiplied by 10 is moving the decimal place. Is equal to 0.3x plus 5. And this looks just like a quadratic equation, so let's just group everything on one side and set the other side equal to 0. So I'm going to subtract 0.3x from both sides. Subtracting 0.3 from 4 leaves me with plus 3.7x minus 5 equals 0. Cool, so we've got this quadratic equation to solve. Because I don't have nice numbers here, my coefficients aren't nice integer values, they're these decimal things, I'm not going to be factoring this. I'm going to go straight to the quadratic equation. So x is going to be minus b minus 3.7 plus or minus the square root of b squared, 3.7 squared minus 4a times minus 0.4 c times minus 5 all over 2 times a minus 0.4. So you'd plug this into a calculator, you'd evaluate this, and here's what I get. I got, after rounding to 2 decimal places as the question desired, 1.64 and 7.61. Alright, so there are the 2 points of equality between these 2 functions. So now I'm just trying to make some space here so that I can graph this. Let's see what we have. So now I want to draw a graph. Remember, we're only going from 0 to 10. I don't care about x values outside of that. Graphing g is easy because g is a linear function. It's a straight line. It's got slope 0.3 and it's got x or y-intercept of 5. So we'll call this 5. Got slope 0.3, something like this. And if you really want, I can give you the y value on this other side. When x is 10, this is going to be 0.3 times 10, which is 3, plus 5. This corresponding y value over here, that's 8. Okay, so there's g of x. It's this linear function. The reason I need equality is so that I can draw this next part. I need to know when f is equal to g, so I can draw this next part accurately. Remember, if I just expand this out, this looks like minus 0.4 x squared plus 4x. That's a quadratic, so I know it's a parabola. It's a downward opening parabola. So theoretically, it could look something like this. And it could never intersect this graph at all. There could be no points where it's equal to each other. But I know that it does have 2 points of equality. And they intersect at 1.64 and 7.61. So maybe something like this. Okay, so I know that if I have a downward opening parabola that cuts through at these 2 points, then my function, my parabola must look something like this. Again, I'm not getting the x-intercepts or y-intercepts here accurate or anything. I just know I generally have a parabola that looks like this. Opens downwards and cuts through at these 2 points. Why are we doing this? Well, this might sort of correspond to some sort of cost functions. You might be asking, what's my break-even points? When is the revenue positive, or something like that? So here's the next question, part B. When is f of x bigger than? Actually, let's just go strictly bigger than g of x. Well, remember, f of x is this function in red, minus 0.4x times x minus 10. So now that I know where they're equal to each other, and I know what my graph looks like, I have this picture, asking when is f of x bigger than g of x amounts to just looking at this picture. Well, it's bigger along here. So between these two x values. So the answer is between these two break-even points. 1.6, the interval 1.64 to 7.61. And I'm going round brackets there. I don't want to include the endpoints because it was when is f of x strictly bigger than g of x. At the two endpoints, they're actually equal to each other. So if I wanted to solve this inequality, when is f of x bigger than g of x, what I had to do was figure out where they're equal, and then draw this picture to identify where, in which region f is bigger than g. And similarly, when is f of x less than g of x? Well, we've already done all the work that we need. The solution, in this case, is, remember, we're not going off to minus infinity here, we're just going from 0. So it's less from 0 to 1.2, or 1.64, sorry. 0 to 1.64, and, so we use our union notation, and 7.61 to 10. Actually, our domain said we included 0 and 10 in the domain, so I'm going to put square brackets on the end here. It is strictly less than including 0, and strictly less than at 10 as well, so including 10. So again, we're just sort of doing math here, but if we gave these real-world interpretations, maybe, for example, maybe there's a linear function, the white line g of x, maybe that's a cost function, and the red line is a revenue function. Well, these two equal points would be your break-even points when the cost is equal to the revenue. But everything in between, so maybe some number of units sold in between 1.64 and then 7.61, that would be the region you'd want to hit to actually be in a positive profit region. Meanwhile, outside of these two regions, that would give you, of course, negative profit. There's other ways we can sort of pose these in an application sense. Again, maybe you're given some sort of profit function, and your profit function is a quadratic. So you know your profit function looks like a parabola, and the question is, how do we maximize profit? Well, maximum profit occurs, of course, at the peak of the parabola, at the vertex. So that question would amount to just take your quadratic function and find the vertex. And the y value of the y coordinate of the vertex would be your maximum value, or your maximum profit that you can attain, and it occurs at the number of units corresponding to the x coordinate. Otherwise, we'll stop here. Thanks.